Welcome to Radar System course. We continue discussion on a clutter attenuation. So we have learned that earlier a delay line canceller. There are the limitations of a delay line canceller is it's not able to attenuate a clutter from the finite spectrum. Okay, so to avoid it, we supposed to use a clutter attenuation here, the technique. Now, what are the consequences of a finite with clutter spectrum that we will see? We can obtain that the equation of the clutter power spectral density function, that is W of f, with respect to the using the Gaussian function. Now we'll consider that what will be the frequency response of a single delay line canceller and a double delay line canceller. Okay, so already we have learned that a single delay line canceller and a double delay line canceller. Okay, so we have seen that there will be a delay line canceller that is to be considered to avoid the a clutter. Okay, that is about a stationary clutter. Now we can consider that what will be the clutter spectrum and what will be the single delay line cancellation here. Okay. Okay, so this one is about, we can say that this one is about a clutter spectrum. This one is about a clutter spectrum now. Okay, this one is about a clutter spectrum. Then we have this one is about a single cancellation. This one is about a single cancellation. This one is about a double cancellation. This one is about a frequency. You can say that FP, FP. This one is about a twice M. Okay. Okay, this one is about FP, then about type twice FP. Now this one is the frequency response. Here we can say that of a single delay line canceller. If you see that this one is about a single delay line canceller, it is about to see through this blue line, and double cancellation from the red, and this one is about from the black. You can see that it is about a clutter frequency. Okay, clutter spectrum. So now if you consider that the expression of the power spectral density here, okay, so what happened generally, some of the clutter is not able to remove, so in that case that clutter will occur. Okay, that clutter will occur across this on the display device there. Okay, so but what happened here, if we consider that only stationary clutters will be removed and some of the clutters are there that will not be removed. So that can be displayed on the display device. Now our aim is about to remove those clutters there. So that will be on this display devices. So, so to remove that, so we can consider that what will be the a standard deviation and what will be the value of a standard deviation with respect to a frequency. So if we consider that standard deviation value will be greater, so in that case the sigma c will be greater. In that case the amount of the clutter that will be passed by the filter that will be interfere with a moving target detection. Okay, this will be a large. So then this will be, if this will be a large, so W of F means we are getting the clutter there, and this will interfere with a moving target. So clutter attenuation is produced by a single delay line canceller. If you consider that, that will be with respect to what, a W of F, and a W of F with respect to what will be the response H of F. Okay, frequency response of the clutter attenuation. Okay. In that case, if we consider that a single delay line canceller will just eliminate a target. But if you consider that a double delay line canceller, so it will remove the, okay, more amount of clutter there. Okay, so larger the amount of clutter. Just like we can say that what will be the amount of clutter that will be rejected, okay, by this delay line canceller. That now we can calculate that what will be the clutter attenuation. Clutter attenuation CA is equal to what, with respect to spectral density of a clutter W of F in with that. It is depending upon the frequency. So that's why you can say that it is about a frequency now. Okay. So 0 to this one WF H of F. Okay, this was about H of F. We have H of F is about a frequency response. Okay, that we have seen earlier. Okay, this one is about a, for a given particular delay line cancel. If we substitute the values of this W of F, so we will get that a clutter attenuation with respect to the, what will be the standard deviation. Okay, what will be the standard deviation value. So if I replace that, earlier we have seen that WF is equal to what, W of F is equal to W0 exponential of minus F square by twice of sigma c square. If we are writing this expression WF, and if we are solving for the given particular pulse repetition frequency TP, okay, so what we are getting is CA is equal to approximately is equal to FP by 4 pi square sigma square C square is equal to FP square, sorry, here FP square lambda square 16 pi square sigma C square. Okay, this is about a clutter attenuation. See. Now, if you consider that this clutter attenuation, it is depending upon that what will be the a pulse repetition frequency. Okay, this one is depending upon the pulse repetition frequency. If you replace that a pulse repetition frequency with respect to a pulse repetition period time TPM, so we can write here a clutter attenuation. But if you consider that a clutter attenuation by the single delay line canceller, it is not sufficient, we say earlier. Okay, it is not sufficient. So there will be blind spot. Okay, so some targets are there, those have the same repetition frequencies are there, so that will not be avoided. Okay, so we can say that there are the limitations of a single delay line canceller. So to avoid it, okay, what are the limitations single delay canceller? Because some clutters not to be removed there. So to avoid it, we can use, instead of a single delay line canceller, we will use a second delay line canceller in a cascaded. Okay, so we can say that single delay line canceller, then a double line canceller. Okay, it is in a cascade form. And then when we are using the second delay line canceller in a cascade, then the frequency response function, that we can say that H of F of this two delay line canceller, because it is in a cascade one. So it will be what? a square of the a single delay line cancellor. So earlier we have said that h of f is equal to what? Twice of sine. Okay, so instead of that we can say that it will be a square of this one. So we can say that 4 sine square by f t. Okay, 4 sine square by f t. Okay, that is about a frequency response. Now, if you consider that this 4 pi f, and that earlier we have said that the response we have the clutter attenuation. Okay, you can say that another one, this is about a dotted one. Okay, that whatever the line we have obtained. So in that case, whatever the curve we are getting, okay, that curve from this particular frequency response that can be removed. We can say that clutter attenuation will be possible for the double delay line cancel. Instead of a single delay line canceller, so we can use a double delay line canceller. So we can say that the clutter which has the frequency spectrum with a double delay line canceller, that will attenuate more of the clutter there. Okay, so that's why we can say that a clutter attenuation using a double delay line canceller, so it will be approximately is equal to what? fp4 by 48 pi square sigma 6, sorry, square root to 4 because it is about a square earlier, is equal to fp raised to 4 raised to 4 lambda raised to 4 divided by 768 pi raised to 4 sigma b raised to 4. Okay, this one. Instead of a square, there will be what? Raised to 4. Okay, this term. So that is because of a additional delay line canceller we are using. That additional delay line canceller that will be in a cascade here, so that we are getting the frequency response h of f. If we are using a 2, so that the response will be a square of it. So that's why a 4 sine square, a sine square term, because it is about a square. So if we are using a nth power of a single delay line canceller instead of a second one, if we are using a nth, okay, nth number of a delay line canceller in a cascade. Okay, so in that case, what happened? So there will be a nth power there. Okay, so in that case, the clutter attenuation that will be occur in terms of a nth. Okay, that will be in the a cascade form. So earlier, what we can say that in a clutter attenuation equation, okay, so we can say that we have a clutter attenuation equation that is about twice of sine pi ftp. Okay, so instead of that, we can say that there will be 2 raised to n sine raised to n. Okay, that will be the of a nth power. Okay, that will be the delay line canceller. So we can use multiple instead of single delay line canceller, 2 delay line canceller, or a nth delay line canceller in a cascaded to remove the or to attenuate the clutter information. So to calculate that, what will be the to identify how much will be the clutter attenuation takes place. So we need to calculate that MTI improvement factor. Okay, MTI improvement factor. So what will be the MTI improvement factor? Because we are using a clutter, means we are cancelling the clutter using the multiple delay line canceller. Okay, so MTI radar is cancelling a clutter there. Okay, so what will be the clutter attenuation is to be takes place? If we have the nth delay line canceller, so there will be the nth time clutter attenuation takes place. Okay, nth clutters to be cancelled there. So in that case, we need to find out what will be the MTI improvement factor. So MTI improvement factor that will be depending upon that what will be the clutter attribution. So in that case, so it will be depend upon that what will be the signal to clutter ratio at the output of a clutter filter. Okay, what will be the signal? What will be the signal to clutter? Okay, you can say that we are getting a signal to clutter ratio at a output here. So what will be the ratio we are getting across this output from the given particular filter? Okay, from the given particular filter. So after filter, what will the signal clutter output with respect to what? What will be the signal to clutter input we have given earlier? What will be the input we have? Okay, and that will give you the MTI improvement factor IF. Okay, or you can say that improvement factor. Okay, this one is about improvement factor, that is called as the IF. Okay. Improvement factor IF is equal to what? A signal to clutter output ratio with a signal to clutter ratio at the input of the clutter filter. What will be the signal to clutter ratio input at the filter to the signal to clutter ratio across the output of the filter there. And this will provide you the a improvement factor. So improvement factor is nothing but what? What will be the clutter in, the clutter out into signal out by signal in at a given particular Doppler shift. Okay, so everything will be at a Doppler. So we will get that a clutter attenuation. Okay, into the what will be the average gain. Okay, so this will give us the improvement factor is nothing but what is equal to a clutter attenuation into a, that is CA in by C out, that is nothing but a clutter output, and this S out by S in, that is nothing but a gain. So we can place there CA by C out is nothing but a clutter attenuation. Okay, this is C in by C out, nothing but a clutter attenuation, and this S out by Sn is nothing but the again. So we will get that a improvement factor IF with respect to clutter attenuation and what will be the average gain of the device there. And that average gain, it is depending upon that response of a filter, that is about H of F. Okay. So what will be the average gain of a single D line canceller? Generally, the average gain of a single D line canceller is a 2. If we are using a double D line canceller, so then it will be a 6 then. Okay. So then what will be the improvement factor for the single D line canceller as well as a double D line canceller? So if I consider that improvement factor for the single delay line canceller, okay, IF for what? A single delay line canceller is equal to, or you can say that approximately 1 by twice pi square sigma C by FP bracket, or we can write equal to lambda square by 8 pi square into sigma V by FP bracket. Okay, this one 8 pi square sigma V by FP. Then improvement factor, if we have a delay line cancellor, double delay line cancellor is equal to, so it will be 6 times. So that's why you can say that 1 by 8 of pi raised to 4 sigma C by FP bracket raised to 4 is equal to lambda raised to 4 by 128 pi raised to 4 sigma V by FP bracket raised to 4. Okay, this one sigma V by FP bracket raised to 4. So this way we will get that a improvement factor in terms of a double line. If there will be the nth delay line cancellors. Okay, so what will happen? The IF factor will be what? In terms of what? Instead of that, we write a nth here. Okay, nth order of filter. So we will get that a improvement factor. So instead of that, we can write the improvement factor for the nth delay line cancellor. So we can write here improvement factor for the nth n cascade delay line cancellor. Okay, so in that case, approximately we can write 2 raised to n, 2 raised to n factorial 1 by twice by sigma c by fp raised to twice n. This one. This one is about the improvement factor for the nth cascade is equal to approximately 2 raised to n by n factorial into 1 by twice by sigma c by fp raised to twice n. Sigma c, it is in earlier standard deviation. It used to be used anyhow. So we can say that instead of a single delay line canceller, there will be a nth delay line canceller. Okay, so there will be a nth delay line canceller. So you can consider that clutter attenuation that will be depending upon that what will be the ratio of sigma c by f. Okay, so if this ratio is small, then improvement factor will be large. Okay, so it is depending upon that sigma c by f. Okay, so we can say that for a nth delay line canceller, so what will be the ratio of this particular factor sigma c by f a? That will decide you the what will be the improvement factor value. So we will see that a double delay line canceller. So we have seen that a single delay line canceller earlier. So we'll see that a double delay line canceller. Okay. So we can talk about that n pulse delay line canceller. Okay. So we have seen earlier that is about a single delay line canceller. So input now. Input is to be given delay now. This one is about a first delay line. In that case, you can say that delay line t is equal to 1 by f. Okay, so then we will get the output from this now, and this will be the input. We are getting the output from this. This will be the input. We are just summing it. Okay, that summation text that here -1 +1. Okay, and then again we have another delay line cancel, and again the frequency is about the same. That is about t is equal to 1 by f. Then again, then with the delayed out, this one is about delayed output, then it will be summed here. Okay, and then we will get the output. This one is about what? A two delay line cancel. Okay, one delay line cancel, another delay. So it is in a cascade form. So now if we have a three pulse canceller, so what will be the three pulse canceller? So we can consider that input now. This one is about the input. For the input, we will use delay line canceller now. That is about t is equal to what? 1 by fp now. Okay. So then another delay line. Here we can say that T is equal to 1 by Fp. Okay, so that is about another delay line. We will say that the input is given here for the summation. Now this one is about the output from the delay one, and then we are getting the another input from this delay. This one is about we are getting that a 3 here. So this one is about a plus 1 minus 2 here. This is a plus 1, then minus 1. This one is about a plus 1. Okay, so like that, same. Okay, so yeah, same. But here we are using a 2 delay line, but we have a configuration, so it will provide you the 3 pulse canceller. So this will be the output of a 3 pulse canceller. So we can consider that a nth delay line cancel. So and we'll get the nth delay out. Okay, so nth delay line cancel. So another one is about example. If you consider that, so what will be the input for each and every pulse canceller here? So this one is about 2 delay line cancel. So input for this, and then we will get the output. So at this particular place, so output is depending upon that delay line 1 and delay line 2. Okay, summation of this one, then again this one. Yeah. But here in the case of what? It is just like the output of all these three. Okay, this one here. So we can consider here. So what will be the output we consider? So here we are just applying the weight, just like we are applying the weight -1 and +1 here. We are applying the weight of what? 1 minus 2. So we can apply the different weights for the different inputs, so that we'll get the given output here. Okay, so we can use the different weights for the three pulses, and then we will find out what will be the output for the given particular weight for this 3 pulse catheter. Okay, so if I suppose to consider that the weight is supposed to be a +1 -2, +1 -2 and a +1 now. These are nothing but the weight. Then what will be the output? So we can say that output will be what? S of t, okay, minus twice of S of t plus Tp here, plus, because this one is about a plus here. So that's why we can say that S of t plus twice of Tp. Okay, so this way we can consider it. So here 1. Okay, so different weights we are applying, so we are getting the output. So, whatever the double delay line cancellers we are using, this one or this one, so we are just getting the same output. So if we have a 4 pulse canceller, so instead of a 3 pulse canceller, so instead of that there will be a 4 pulse canceller, and we have a different weight. So what will be the output? So similarly we can write the output for the different delay line canceller. Okay, different nth pulse. Okay, nth pulse canceller there. Okay, so nth pulse canceller which has the same frequency response as the nth single delay line canceller. Okay, so this two delay line canceller and this three pulse canceller. Okay, so it is now both are same now. So if we consider that a nth pulse canceller, so that frequency response of that particular nth pulse canceller is same as the n single delay line canceller. Those are in a cascade there. So we can say that if there will be the larger the number of delay line cancellers we are using, okay, or nth number of delay line cancellers or nth pulse cancellers we are using, so then the attenuation will be larger. So clutter attenuations, what we can say that it will be larger if we are using a multi nth delay line canceller there. Okay. Then another way we can use instead of a delay line there, so we can use a filter. Okay, so that filters which have a nth delay lines present there. we can consider to remove the clutter attenuation. Transversal filter, and this transversal filter is a non-recursive one. Earlier case we have seen that a recursive filter. This one is about a non-recursive filter. Okay, so we have a transversal filter that we have seen earlier. That is about a 3-line pulse canceller. Similarly, we can find out here the nth delay line canceller. Okay, and that nth delay line is to be used as a transversal filter there. Okay, so 3 pulse canceller earlier we have seen. That's again the example of a transversal filter. If we consider that in general there we have the n delay line, then the weight is to be applied to the given pulses, and then we combine this one, and so that we'll get that a transversal filter, and that will be operated in a time domain. And for each and every transversal filter, if supposed to be we are using a taps with a weight, so then we'll get a output after summing it, and that output is depending upon the what will be the delay we apply to this particular transversal. So this particular filter is nothing but a non-recursive filter, or you can say that feed forward, or a infinite pulse repetition filter, or a finite memory filter. So just I suppose to draw this transversal filter here now. We have input now. Okay, this one is about input. Then we apply the delay. You can say that T1, delay 2, delay 3 now. Okay, delay n. Okay, so we can say that T1, T2, T3, Tn minus 1. Okay, that's about a delay. And for each and every delay, we are supposed to apply a given weight. Okay, it has a feed forward tap with a weights now. This one is about a weight 1, weight 2, weight 3, weight 4. I can say that okay, Wn. Okay, this one is about weight n. And then add this one. Okay, summation of all this. These are the different tabs we have. We have a summation text summer, and we'll get the output. Okay, after that we'll get the output. So here we can consider that we are applying the weights to the n plus 1 pulse, and then combine here. Okay, these are the delayed with n plus 1. Okay, we can say that that's what we can say, that we have a delayed here, and then we are applying okay, weight for each and every pulse, and we'll get the output of this. This is nothing but a transversal filter with the feed forward lines. Okay, so we have feed forward lines, and it has the taps, and it has the particular weights there. Okay, so these are about what we can say a filter, or we can use a different filters at a different filter frequency range. Okay, so earlier we have said that sine square of what we can say that pi ftp. Okay, so instead of that, a filter, generally a transversal filter, again it will operate with a sine of pi ftp frequency. But again, if we consider the different filters, or a optimum filter, if supposed to use a optimum filter, so then we will use the same filter for the clutter attenuation, and in that case the filter is called as the optimum MTI filter for a given specific frequency. So it will improve the factor of that nth pulse delay canceller with a given particular weight, and that weight we consider here for a given particular frequency response. So criteria to define, so what will be the MTI improvement factor. Okay, and that based on that MTI improvement factors we can design the optimum filter with a function of sine of, earlier we can say that nth of pi f dp. Okay, so this way we can design a transversal filter. So that is about what we can say different configurations we can use here, and that different configuration is used to remove the delay. So another example we have, there will be the delay line filter with both feed forward and a feedback there. Okay, so generally a recursive filters we are using in a recursive filter. So and in non-recursive filter, what will be the combination there? So in that case, it allows some particular frequency response for the given particular plane. Okay, so I'll just consider here a different the recursive delay line filter. We can consider that for the nth pulse there, and we can say that there will be the input V in now. It is about the input V in, and that will be given to the delay now. Delay 1, delay 2 here. And then we supposed to sum of all these ones. Okay, all the delays to be sum of them. Getting the input from one. Okay, so like this one. We are getting the input. And then we can consider that the input from each and every component now. Consider that what we are getting after delay is one. Okay, so this one. And then we will get the output here. This one is about the configurations. We can say that will work in a time domain filter with both feedback, this one feedback as well as the feed forward. Okay. So this configuration we consider that for the attenuation. And this particular filter provides a more flexibility in shaping the frequency response, so that we'll get a better response than the non-recursive filter there. And again we have used a fewer delay line, okay, to avoid that a cutter there. So we can remove that a large discrete clutter echoes, interference pulses from a nearby radar, as well as a deliberate pulses, that will be the jamming pulses or the whichever the pulses that from the nearby object that can be removed through this particular filter there. Okay, so these are about the we can say that uh, use of this delay line filter there. And again a delay line filter, it is depending upon the what will be the frequency response it will work. So generally we can say that it will work at a given pulse repetition frequencies. So what will be the frequency response of the given particular pulse that will be generated across the output of the filter from a single particular pulse through the given particular feedback. Based on that, we can consider that a attenuation there. Okay, clutter attenuation will be taken. So if you consider that in terms of a frequency response from the different filters, so what will be the gain, power gain? Okay, so if we are getting the output, so if I consider here with respect to a frequency response here, okay, this one is about a frequency response, and this one is about a gain. So if you consider that a recursive filter has this particular gain, and a non-recursive filter has a higher gain. Okay, so that's about we can consider, we can say that we can use a cluttering mode. Again, we can use a multiple staggered PRA. Okay, that will increase the what will limitations of that, whatever we can avoid that blind speed, or we can use that whatever the limitations of the filters to be used in a given particular frequency response. So instead of that, we can use a PRA, there, multiple staggered PRA. And we can say that we can conclude here the multiple delay line canceller, or we can say that n pulse canceller, or a transversal filters, or we can say that recursive filters, all are work in a time domain filters rather than the frequency domain filter. And generally, in a Doppler filter bank, if you see in Doppler filter bank, a time domain filter is chosen. Okay. So with this, we stop here and we'll continue again next lecture. So thank you all of you. Thank you all.